Okay, hello everyone. Thank you for joining GeoScience and GeoEnergy webinar of 16th of July 2020. It is our pleasure to host you this week again with another talk. Sebastian is on holidays. Well, to be precise, he's actually in the mountains, so we can trust him. He's going to do some field work too, so that's why he's allowed to skip this lecture. But I have the pleasure and honor to have a colleague of us, Andreas Busch, whom you see on the screen with me today to host the webinar of this week. Andreas is also from Heriot-Watt, where Sebastian is, and I'm also from TU Delft, you know. We are especially grateful to our keynote speakers who have supported this initiative, and we would like to thank them all again, and to you all for joining us and combat work from home isolation, especially to those of you who are on vacation or a staycation, and now you're connecting with us as well with family. I hope that everybody enjoys this webinar as well. And also to you all again for joining us. And please subscribe to our YouTube channel, help us spread the words. All previous lectures are available on our YouTube channel. If you subscribe to our channel, you will see the upcoming talks automatically as well. Also to our student attendees, please attend Porous Media Tea Time Talks series to share your research and broaden your network. Now to the lecture of this week. We are pleased and honored to announce our keynote speaker of this week is Professor Veerle Cnudde. She is with us today. Thanks a lot, Veerle, for accepting our invitation despite being so busy. Veerle received, I read a few lines about her. You know that she doesn't need my introduction anyhow. Veerle received her PhD in geology from Ghent University in Belgium, where she is working today, where she became a research professor also in 2010 and later in 2015, associate professor. And finally, 2018, she became full professor there. She's team leader of Progress, the Pore-Scale processes in Geo-Materials research group, and is one of the coordinators of the Ghent University Expertise Center for Xray tomography, UGCT. She specializes in non-destructive imaging of geomaterials and has a strong expertise in real-time imaging of processes in the pore space using X-ray imaging techniques. Research projects which she has initiated are strongly linked to weathering and fluid flow processes of porous sedimentary rocks, as well as conservation of building stones as well. In the past 10 years, she has mentored a number of students and postdoc researchers, 11 postdocs, 10 PhD candidates, and many, many. And today her group is hosting a lot of researchers for postdocs, 18 PhD candidates. So it's quite an active research field which she is leading. Veerle has published many actually journal articles, more than 170 peer-reviewed journal articles. Since 2012, she is invited member of the Proposal Review Committee of Tomcat and CSA-XMS beamlines of the Swiss synchrotron. As of 2019, she is the new chair of the Proposal Review Committee of the Tomcat beamline at Swiss Light Source for the next 3 years. She's gonna keep that position. In 2008, she was one of the founders of the UGCT spin-off Inside Matters, which is now part of TESCAN. Since 2018, she is Director Research and Valorization at University of Ghent as a member of the faculty board of the Faculty of Sciences. In 2019, she became holder of the chair on porous media imaging techniques and obtained a dual professorship as full professor at the Environmental Hydrogeology Group at the University of Utrecht in the Netherlands. The Interpor Award Committee selected her as the Kimberly Clark Distinguished Lectureship awardee of 2020. She delivered a couple of these lectures. Unfortunately, due to this pandemic situation, a couple of them were actually affected by this. But we are so pleased and honored and happy and glad that she accepted our invitation, as she is with us this week and is going to deliver the talk about the Pore-Scale imaging and understanding the processes in geomaterials. To the audience, please note her lecture will last for about 35 minutes. and followed then by questions and discussions. Like before, please type in your questions in the chat room, and Andreas kindly accepted to chair the discussion session. Thank you very much, Andreas, and he's going to chair the discussion after the lecture. Veerle, thanks once more. The stage, screen, everything, the bandwidth is all yours. Please.
Thank you. Thank you, Hadi, and thank you for this kind introduction. And I'm very honored to be invited to talk to you all today about pore-scale processes in geomaterials. And if you think about pore-scale processes, I could talk about many topics. Could be on fluid flow of reservoir rocks, sedimentation and the agenesis of rocks, fracture formation. But today I will focus a bit more on weathering of rocks. And so if you look to rock weathering, you will see that this is a combination of physical, chemical, and biological processes happening on these rocks. And these have a constant effect on our planet. These processes affect subsurface stability, aquifer and reservoir rock permeability. They have an impact when you want to do enhanced CO2 storage, but also weathering has an important impact on our building infrastructure, as masonry is also damaged by physical, chemical, and biological processes. So when a researcher studies rock weathering, what they typically do, they go to a quarry or an outcrop, or they go to a monument, and they first do macroscopical observations. And after doing that, they often take subsamples, they go to the lab, and then what they first do is they try to characterize the material using different techniques. They test the performance and use of the material, and they try also to get an idea about the durability of the materials, because therefore they use a standardized accelerated weathering test, and this is with the aim to examine how a stone will behave in the future related to, for instance, cycles of freeze-thaw. However, when you look to the results of durability tests in lab and you look to the reality of durability of rocks, you see that there is a discrepancy between both. And this is because it's very difficult to predict rock weathering behavior, because it is an interaction of different aspects. So chemical composition of the material and the structural characteristics are important, but also in reality, you are facing with different processes happening at the same time. The way of the changes in the speed of changes in temperature or relative humidity in reality are different than in the lab. In reality, sometimes rocks are semi-saturated, while in the lab, the experiments are done on fully saturated or unsaturated samples. So it's a very complex system. And if you really want to be able to understand and predict the macroscopical behavior of a rock, you need to have insights. You need to know the 3D microstructure and chemical composition of your rock, and you also need to understand the 3D dynamical processes or the pore-scale processes, what is happening on a pore-scale level, and how does it then affect the macro scale. So you need integrated experiments at high resolution, and you need to be able to see processes dynamically inside a stone. So the way we do this is by using X-rays, and X-rays were discovered by Röntgen in 1895. And unlike visible light, X-rays can penetrate matter. So therefore, they're ideally suited for internal inspection of objects. And what you see when you have an X-ray radiograph is you see contrast, which depends on the density and the average atomic number of your materials in question. So this allows you to look inside your rock. So if you are probably most familiar with X-ray radiography, which is used, for instance, if your arm is broken. Therefore, in order to do so, you need an X-ray source and an X-ray detector, and you put your stone sample, in this case, in the middle, and then you get a 2D representation of your 3D object on your X-ray detector. However, if you want to look to pore-scale processes, this X-ray radiography alone is not enough to give you the needed information. So then the good thing is that in the late 60s, 1960s, early 70s, Cormack and Hounsfield developed a first CT or computed tomography scanner, for which they also got a Nobel Prize for medicine. And in the early developments were mainly focused on medical diagnostic imaging in order to image the body of a person in 3D. But it was by the end of the 70s that this was also used for in more an industrial environment, and that you see the first publications coming where scientists are using this technology to study valuable material, for instance. So what is the principle? For X-ray tomography, you also just need an X-ray source and an X-ray detector, just like what you do with X-ray radiography. But in this case, what you do is you rotate your sample. In a medical scanner, it's the source and detector that are rotating around your patient, while often in lab environment, the CT systems have a source and a detector which are fixed, and they rotate their sample. And what you do is you register a stack of radiographs while your sample is rotating. And your X-ray detector then registers the intensity which is depending of the original intensity coming from your source, and then also the interaction of your X-rays with your material. And this is explained in the law of Lambert-Beer, where you see also the impact of mu, which is the linear attenuation coefficient, which is depending on the average on the average density of your material and the average atomic number of your material, as well as X, which is in this case the path length of which the X-rays have to penetrate through your sample. So the thicker your material is and the higher your average linear attenuation coefficient will be, the less the intensity will be of your X-ray source, of your source coming out. So that is very important. So we are limited. We cannot go for infinite big samples when using X-rays. And that is one of the reasons why when looking at dense materials or rocks, that we already try to go for a limited diameter of our samples. So after having a stack of radiographs, we need to go for the 2D and 3D images. And we do this by reconstructing the signal. So if you have your X-ray source, and here on this left, you have a scheme showing what is happening really, is you have an X-ray source and you have an X-ray signal that is printed on your detector, and here you have your sample. This X-ray signal is taken here at one location, but in reality we have this over each, while rotating our sample, we have this at each location, and then you back project the information of your X-ray signal back, and this allows you to reconstruct your original object in a non-destructive way. So in reality, you take a series of radiographs, then you reconstruct your image, then it allows you to have a 2D reconstruction of your sample. In reality, we have information of your entire volume, so we are able to reconstruct all those slices, and this is then used to render a 3D volume. So like here, a Savonnière, a limestone, a French limestone, which you can see in 3D in a non-destructive way. So the benefits of using X-rays is that you do not have to do a sample preparation, for instance. And so after, if you have this principle, you can start to investigate samples. So here you have an example of two Belgian sandstones taken from Belgium, and you see that their diameter is, their dimensions are in a few centimeters, and you immediately see macroscopically that you see some fractures, and you see also some layers of which are more iron rich. So if you put those in a medical scanner, you will see the fractures in 3D, so you can follow those clearly, and you can also see where you have the iron-rich layers, which have a higher contrast compared to the quartz layers in between. So this is already giving important information of the structure of your material and composition. But of course, if you want to go for pore-scale processes, this resolution is not high enough. So typically we go to micro-CT, where we take samples which have a smaller diameter, and by going to smaller diameters, we gain in resolution, and we can see the individual grains, we can see the individual pores inside our rock. And to explain you the principle of resolution, I have here a scheme where I show all the important features to determine the resolution of a system. So what is influencing the resolution? That is the spot size of your X-ray source, S, the resolution of your detector, and then the magnification. And the magnification of your system is depending on the distance between your source and detector and the distance between your source and your object. So if you have a large sample, you want to scan this, what you will try to do is you will position it in such a way that during rotation, it remains in the field of view between your X-ray source and your detector. And so you will position it rather far away from your X-ray source in order to visualize this completely. While if you have a small sample, you can put this closer to your X-ray source. This way you get a higher magnification, and this allows you to have also a better resolution. And that is why when you look to CT research, often the samples are rather small, because what we want to do is we want to image them at the highest resolution possible. And so we try to find an optimal sample size compared to the obtained resolution. We have in the Center for X-ray Tomography of Ghent University several scanners, each with different sources, detectors. Some have X-ray sources with small focal spot, others with a bigger focal spot, but then able to scan at a higher energy. We have detectors sensitive for high energy, for low energy. So we have this combination because it allows us to get always the optimal image quality needed for what we want to see. And they were all built in-house. So if we want to study rock weathering, we first want to know, of course, the microstructure and of our material. So we need to have multiscale 3D imaging. So typically when you study stones, a geologist will take thin sections, and here you have some examples of 3 French limestones, which are typically used as building stones. And if you put a piece of those rocks in a CT scanner, you will get a similar 3D structure like I can show you here, but with the advantage that it's not a 2D image, but you can look at this in 3D and you have all the slices of your object. So this is already an important benefit. And so what we typically do is we first scan a sample at a lower resolution to have an overview of our sample, and then depending on if we have interesting zones, we take subsamples and then we go for higher resolutions, and we combine this with other 3D imaging techniques. Like, for instance, if you have a microplug, in this case, that you scan at the highest resolution with your CT system, sometimes this is not enough and you need to go for higher resolution. Then we combine this with other techniques. One of those techniques, for instance, is focused ion beam scanning electron microscopy. And with this technique, with the focused ion beam, you etch the block a little bit of your material away, and then you take an image with a scanning electron microscope. And this allows you to take a series of some images by etching some material away. So you get a 3D data set, but it is in a destructive way. So to image dynamic pore-scale processes, that is not the way to do so, but it allows you to get a detailed 3D representation of a small volume of your rock. If you want to go for non-destructive 3D imaging at high resolution and be able to also control, for instance, the environment around your sample. You can go for nano. Well, you have different names for it. So it's plycographic tomography or X-ray phase nanotomography. This is done at the synchrotron, and we did this at the CESAX beamline, so coherent small angle X-ray scattering beamline at PSI. And there we could get resolutions up to 60 nanometer in 3D in a non-destructive way. And it also gave us chemical information. So for more details, I refer to the article of Anna Diaz. But in principle, what you do is you record the grid of overlapping diffraction patterns for many angles, and this is all then stored in order to reconstruct at high resolution your image. So typically this only works for small samples. So our sample was 40 micron in diameter, but then we were able to go for in 3D in resolutions of 45 nanometer resolution. So you can see a lot of details. We could see also that there was liquid inside. You can see even the contact angle of your sample, and this in a non-destructive way. So with this technology, you can go for high resolution quantitative porosity analysis, but on limited volume, of course. But it also allows you to control the conditions around your sample. So we were measuring, for instance, the expansion of clay minerals, and we were scanning it in a wet condition and in a dry condition, and we were seeing how these clays were behaving. And this technique also allows you to do chemical analysis. And so, for instance, we analyzed the liquid that we could clearly see here inside. And this, based on the quantitative measurements of the electron density and mass density, we were able to say that this liquid was the glue inside our pores. So the glue that was used to put our sample on our sample holder. So you get also chemical information. But what you see is that the higher the resolution, the smaller our samples are getting. And a problem there is that your values are depending on where you take your subsample, and that if you want to study porosity, processes on the Pore-Scale, you need to have a certain volume available, otherwise you have too much effects at the edges of your sample. So in a way, ideally what we want is to have high resolution on large samples. So one of the things that we are therefore currently doing is doing experiments with X-ray grating interferometry in collaboration with the research group of Marco Stampanoni at PSI ETH and several Ghent partners. And what we try to do with tunable gratings is to retrieve the dark field image in order to obtain information of sub-resolution features of our sample. So how does such a setup look like? Here you have a lab-based system where you also have your source, your sample, and your detector, similar like with normal CT, but then you put the gratings in between. And you can position these gratings parallel to each other and away from each other, and by doing so you are influencing the intensity in the pixels is changing while changing the positions of those gratings, and this allows you to obtain the dark field signal. So we did an experiment on a roofing tile, which is a difficult one to image with normal absorption CT, because we know it has a high porosity, 34% in this case, but we know that most of the pores are below 1 micron. And so if we scan this sample, a piece of this tile with normal absorption CT at a voxel size of 8 micron, we see immediately that we only get around 2% of porosity visible. If we take a subsample even smaller, so even a sample of or something around 1 millimeter diameter, we see more porosity already available, and we have a resolution, a voxel size here of 2 micron, but still we are missing a lot of the pores below the resolution. So we tested this grating, tunable grating interferometry at the synchrotron, and here you see what it would potentially could give you. So here on the left you see an absorption image, and where you see zones which contain of clearly big pores, but then you have zones where you cannot say a lot about. If you then look to the dark field image, you see that you have distinct zones, those more black one, which contain less signal, indicating that there you do not have pores of a certain pore size below the resolution of the system. So you can obtain information below the resolution of the system by using those gratings. And now we are working on interpreting the data in order to get a kind of automatic analysis tool for pore size distribution. Besides structure, you also need chemical information. You need 3D chemical characterization. So you can combine, for instance, CT with information of a scanning electron microscope. You can, for instance, polish your surfaces of your rock, you scan it, and then you put it in a scanning electron microscope. You try to get the mapping of all your elements, of all your minerals, and then you combine this with the gray values of your X-ray CT system, and this allows you to get an indication of the composition. Another way what you can do is combine micro-CT with XRF, as XRF is an excellent technique to obtain also some missing information of chemical properties that CT does not provide. So what we did in the past is we took a stone, we first scanned it, and based on the CT, you see that you have different gray values, and those different gray values indicate difference in linear attenuation, so difference in average atomic number and density. But without knowing extra information, we cannot say which mineral is which. So we then put this in a micro XRF system. We did elemental mapping of the surface. We clustered this information and then combined this with the CT data. And this allowed us to combine chemical information with the gray values and get a kind of estimate of where minerals were positioned inside our sample, but based on some estimates. Of course, it's not so ideal that you have to put your sample in different systems. So we built some years ago in close collaborations with the XMI group of Professor Vinci, a Heracles scanner where you have XRF and CT combined. So in this system, we first have a CT system, and then you can automatically go to one of the XRF end stations. One station is an XRF tomography end station, and the other one is an end station for confocal XRF. And so this allows us to first take a sample, scan it, based on the reconstructed image, select an area of interest. For instance, say, okay, I want to have a point analysis at this spot. Then it automatically goes to that spot, does the measurement, and you get the point analysis. Similar, you can also draw a line and do a line profile, or you are able to do mapping of your elements. So here is an example of our Savoniere limestone where we added some gold particles, and based on the micro XRF, we could see that in green is where the location of our gold particles are present in our rock. You can also see that the resolution is not as high as with normal CT, but it has a very strong it can get small amounts of material lighting up very easily. So in this case, our gold nanoparticles were had around 60 nanometer diameter. But what you can also see is that you are missing all the internal information, and that is because XRF typically gives information about the surface and subsurface. And as you can see here, most of the information is like 200 micron below the surface, more or less. And this is also depending on which element that you're looking at. But so there is also a limit. It's more for superficial detection. So another study that we are working on at the moment is combining X-ray CT with hyperspectral imaging. So this is also in literature referred to as color micro CT. And you also just need a source. You have your sample in between. And then what you do is you use a spectroscopic X-ray imaging detector. And those detectors should have sufficient energy resolution to distinguish individual elemental absorption edges. And I will show you what the results could be. And this is a work of one of the PhD students, also in close collaboration with our partners in a European project. And so here we have grains, a mixture of grains where you have quartz, tungsten, gold, and lead. And if you just do normal CT on the radiograph, you can already distinguish some highly attenuating grains. But if you reconstruct, you see bright spots, and those can be lead or gold. But without extra knowledge, it's impossible to say what we are talking about. And so if you do spectral CT, the resolution is a little bit lower, but you can also identify the same grains. And if you then look to the spectrum that was detected by those detectors, you can distinguish the different grains, and you can say, okay, this one is the lead, this one is the tungsten, and this one is the gold sample. So this allows you to get 3D chemical information for certain minerals and elements. So this is also work which is ongoing in order to help us to understand the chemical composition of materials. And once you have the 3D imaging, the multiscale characteristics of the structure and the chemical composition, you can go for fast 4D imaging to study the processes at pore scale. So typically what you need is you need sufficient time resolution. So typically this is done at synchrotrons, because if you take a normal CT scan, it on average can take something like 20 minutes for a fast scan. So this is ideal if you use this system, if you want to go to visualize slow processes and where you can do time-lapse scanning. But if you want to go for fast processes, you need to have, during one scan, everything needs to be stable. So you preferably want to have fast rotations. This is possible at the synchrotron. So like here, I found an article of work at PSI where they did 208 tomographies per second, but you do not always have access full time to a synchrotron. So we developed a dynamic scanner, our environmental CT scanner, where the source and detector are rotating around our sample, and where we do a full scan in 12 seconds with a focal spot of 5 micron. And the reason why this is gantry based is because we wanted to have, if you want to do studies of processes, often all the wiring and tubing around your sample are becoming more complex than rotating your source and detector around your sample. So similar like in a medical scanner. So that is why we developed it like that. And so we invested in a lot of add-on modules for in situ imaging. So we can do reactive fluid flow. We have tiny climatization rooms. We have a freezing cell. We can do compression, tensile testing, all on our CT scanner, and monitor the processes. So one example is, if we go back to our limestone, is, for instance, if you have your limestone and it's fully saturated with water, and then you inject a salt solution from the bottom, you see that in function of time, certain pores become more green and yellow, and this indicates that the salt solution is getting higher. And so you can see when and where salt is entering inside your system. And salt is a real problem related to weathering of stones. Besides just looking and seeing where the salt is changing, you can, with CT, of course, you have all the 3D information. So you can individually select all the pores and then individually look at how the concentration is changing in an individual pore. And you can also, for instance, monitor when your salt is entering a certain pore at what time. So that is all possible. After you have your salt solution in your rock, you can also look to how it crystallizes. How you can look to how salts crystallize in just when you have your liquid and you see how a salt is crystallizing. But you can also look at the rock itself with the salt solution. And here in green, you see your salt solution, a function of time, and in red, where salt is precipitating in function of time. So you can monitor this and you can quantify this. You can also do repeated cycles of re-wetting. And for instance, if you have your stone and you know where your salt is after one cycle of drying, you can re-wet it and dry it again. And then you will see that your salt is migrating inside your rock. So you can repeat processes and get a better understanding of what is happening inside your rock. Also, you can look for fractures that are occurring and things like that. So with Pore-Scale processes combined with CT, you are able to look and study salt and ice crystallization. You can go to study freeze-thaw cycles and see how fractures are behaving, are occurring when you have, for instance, a saturated rock and you do cycles of freeze-thaw and where those fractures are occurring. You can look for the effect of the acidic environment, reactive fluid flow. Here you have an example of a rock which underwent an acidic environment, and you see a gypsum crust formation, or you see dissolution and wormholing. You can look for biological activity. You can see, for instance, here in this Savoniere, where you have a natural cement being formed by bacteria in yellow. You can follow fracture behavior in function of time related to the structure of your material. And you can study, of course, fluid flow, which is very important when studying weathering of materials. So by combining CT, you're able to characterize everything and even visualize a lot of processes. But of course, this information then needs to be used to be able to model or predict the behavior of your rock in the field or in a building. And what people do is they use the CT information as input for instance, pore network modeling. And I refer to all the work of the modelers that already presented their work or will present in the future their work on these seminars. And because this is where we stop, then the modelers start. But if you have your CT data and you have your model, you're able, for instance, to model how water is being displaced by a non-wetting phase in this case. But we can do the same experiment in lab, and then we can validate if what we see in lab corresponds to the model. And so this allows you to really validate the models and understand the behavior. And so to conclude, I want to say that by using X-ray CT combined with synchrotrons, you have a huge amount of possibilities. If you combine this then with lab experiments, using additional techniques to validate what you have been measuring, you are able to really get an inside view of what is happening. And then this information can all be used for modelers to do the modeling, and what is modeled can be verified with then the experiments. So I think to understand the macroscale behavior of rocks, you need to have an interdisciplinary approach and have people who are strong in experiments and people who are strong in modeling. And the combination makes this that at a certain moment we will be able, based on the Pore-Scale, to identify what is happening on the field scale and predict and even control this behavior. And maybe at the end, hopefully you will have the opportunity to visit us in Ghent and look to our nice buildings and see how they are resisting the weathering if they do this well or not. So I want to thank you for your attention. I want to especially thank all the past and current UGCT members and all our collaborators. It has been an honor to work with all of them, and this is also the result. These collaborations is the result what I was showing now. Thank you very much.
Thank you very much for such an inspiring talk. Especially, I would like to thank Interpore Society for providing this award and all the lectures. I hope the pandemic soon will be resolved and you would visit many places, Veerle, for this lecture in person. I would like to hand over to Andreas, who will chair the discussion session. We already have received quite some questions, and I believe that more will come. So, Andreas, the stage is yours. I'm going to put myself on mute.
Mm-hmm. Thank you, Veerle. Fantastic talk. I learned a lot, like always. So there's a couple of questions, different ones. And maybe we start at the top. And the first question is by Leila Hashemi. And she's asking about the limitations of determining contact angles by using micro-CT, and especially in combination with the chemical composition of the fluid phase.
So, okay, I think, well, we have a PhD student working on determining contact angles, so I would suggest also to look under my name, and we recently published some work on that. But I think the challenge with contact angles, for instance, is that you want to have a sample, which is that you want, where you want to determine the contact angle in between. So you need to have a good resolution, and you need to have enough detail. And then you have also the problem that sometimes those contact angles, they are changing because it's a dynamic process. So it's not so easy, but it's possible. And I would refer to this presentation of Arjan Machini, who worked on this and is currently working on this, but I'm happy to go more in detail with you, maybe more in private then.
So the next question is by Majid. It says Hassani, but I guess this is Majid Hassani Sadeh from Utrecht University. Mm-hmm. So they're apparently looking at the dynamics of ink droplet penetration in paper. So do you see any hope to see that with an imaging system?
I think what I would do, because these are very fast processes, I would suggest to do these at the synchrotron, because they are ideal. You have also some limitations to take into account, because if you spin a sample very fast, it also can have an impact on the fluid behavior, of course. So, but I would suggest to do first experiments at the synchrotron. Another way of looking at liquids is also by using neutron imaging, which is sometimes also a very good tool to work complementary to X-ray imaging.
Does it then help if the ink has a certain composition that helps the imaging?
Sometimes, yeah, it can get because of the composition of the ink, you can have a bigger contrast. But I don't think that it is a problem with paper and ink to visualize both of them and to have the contrast high enough. It would be a problem if you have a water-wet system and you add ink on it, then it can be a problem. But then typically people also play with the chemical composition of the ink or the liquid to have enough contrast.
Mm-hmm. The next question is by Luyu Wang, and the question relates to crack propagation in rocks. I guess that in an experiment, if that can be visualized.
Yes. So everything depends on how fast what you want to see, and so the speed of the processes. So you can do, for instance, compression tests, or you can do many tests in lab. The only thing you need to think of is that, as I said, that the sample size should be as small as possible to have the highest resolution. If you have add-on modules to control your sample or your fracture propagation. These can impact also how close you can put your entire setup to your source and have an impact on the resolution. So you have to see which kind of fractures you want to see, what the dimensions are, and which resolution is needed. But a lot is possible. And if you look to literature, you will see that a lot of people have been working on fracture propagation research using Xray tomography.
There's another question related to mechanics by Kishan Kumar. And the question is relating to a combination of CT measurements with acoustic measurements.
Yeah.
Do you think that would be possible?
Yeah, it's something I really look into, because I think, so that is also one, I didn't put this in this presentation, but I think combining CT with other measurements and combining this is really valuable. So indeed, acoustics is something which is in the back of my mind, to combine this with CT measurements in together, to register them together. Yes.
Right. So Soren Pop asked about soil precipitation, but I think that question has been solved at relatively late in your talk already. So there's a follow-up, and he's asking if you can visualize the precipitation in combination with unsaturated flow or two immiscible flowing phases.
Well, then everything depends on. It depends on the contrast. If what liquids are we talking about? How big the features are that you want to see? How big your volume is that you are scanning? So you have some restrictions where that you need to optimize first in order to say yes, it's possible, or no, it's not possible. So it depends on different aspects here again.
Via Sheslav is asking if the swelling of shales can be visualized.
So if you have a big block, and it all depends on your sample and what resolution that you want to see, and also if there is added value in using CT for this. It also depends on what your question is. Shales, the swelling of shale, will you look at a small subsample, and how does it affect then the behavior? These are all things you need to consider as well, because a bigger sample can have another behavior than if your sample is smaller, for instance. So it depends. If you look at it logically, if your sample has a certain dimension and you can control the environmental conditions, you can look on how it is behaving, and you can do time-lapse scanning if it goes slow, for instance. So these things are possible, but the question is also, what is the added value of doing this with CT then at that moment? What do you want to see? Because if you want to see really detailed features, maybe you do not have the resolution which is high enough to see what you really want to see. So it depends on the question also.
Yeah. I think we once measured clay swelling with Newton diffraction, which worked quite well back then, because that's really looking at the crystal level.
Yeah.
Then there's a question of Santi Chandra. If you think that dual energy CT scanning could also help getting the composition of the rocks, like shales or carbonates or sandstone, whatever.
Yes, I think so. Because I was limited in time, I only talked about a small amount of things, but I think indeed dual energy is one of the techniques that you can also use to visualize certain minerals more clearly. And I think, so what I think is that it's by combining, for instance, dual energy, by combining with spectral CT, with information of XRF, that in the end we will be able to get a kind of automatic 3D petrography of a rock. This is what I hope in the end we will achieve, but it will be a combination, because dual energy works very well for certain things, then it's more difficult for other materials. So but I think it's a combination of different techniques, and for certain, dual energy is indeed one of the techniques that can be used.
Thanks. Then we have a couple of questions from Mustafa Seba. And the first one says, when we scan a sample in a dry and wet state, the gray level changes. How would you manage to differentiate between that for eventual segmentation and porosity evolution measurements?
Okay. Okay, then it depends if your sample remains, if you have your wet sample and the matrix of your grains remains at the same place. So it depends on the material that you're scanning. Like, for instance, if we have rocks where the grains are remaining stationary, even if they are wet or dry, what we then do is we do differential imaging, we subtract and we see where you have the liquid, and that is what we use for then segmentation or, for instance, to study porosity. But if your material is changing while wetting, for instance, if you have paper and you make it wet, or wood and you make it wet, also that structure is changing, and then it becomes more difficult and more challenging. But there are, if you look on Web of Science, you will see that many people are working on these things, specific problems. And so I would suggest also to look there. But what we do is, if your matrix is stable, then we subtract it from each other and look and combine it then.
There's another one from Mustafa, and he's asking if a fluid invades the porous material, some pores get filled and others don't. So in terms of, for instance, salt precipitation, you might get crystals forming in some pores and not in others. Can we differentiate that?
Yes. Okay, so because this is related to the pore structure, and this is also what you observe. So you first determine the pore structure, then you know where you have your fluid going, and then you see. So we could see, for instance, we could quantify in which pores we get salt crystallization and how salt crystals were growing in function of time, related to the pore structure even and the pore body. So you can quantify this. This helps you to have an idea where salt is precipitating in which pores or which pore bodies or pore throats. So yeah, you can quantify this, and this helps you to have an insight in the growing of those crystals inside.
Thanks. I actually have a question, if I may. And that is the limitation on resolution. So,
Mm-hmm.
I mean, do you see any physical limitations in getting better in resolution? I mean, back in the days, micro CT scanner was still basically state of the art, but then there's nano CT scanners coming up. So do you think that in 5 or 10 years' time we are able to resolve down to the nanometer level?
So of course, I'm a geologist, and I applied the technology, and this is in close collaboration with radiation physics. So I think if you ask this question to a radiation physics guy, the answer will be maybe different. But from my point of view, I think what we try to do is to use it in a lab environment. But I think everything what is happening or what is possible at the edge of what is possible is done at the synchrotron. So what we do is we look at what is possible at the synchrotron, and then try to see what we can implement of this technology in lab. And I think for the moment, what is done at the synchrotron is at the edge of what is possible, I think also for the next 5 years. So I think reaching resolutions in the order of several nanometers, what is currently possible, is already an enormous advantage, but it's challenging because these experiments all take a lot of time, and it's a lot of preparation, and a lot of things can also go wrong, and you are limited with certain physical limitations, like, for instance, sample size. Also with grating interferometry, what we are now working on, we will also be limited in sample size, or we will also be able to define a certain composition of samples is possible, these elements and this maximum dimension are possible. So I think it will always be a combination of different technologies. And so that is why I think we really need to work in an interdisciplinary way and use different techniques to answer our questions. And I don't think one technique will answer all.
So you think that in the future it would rather be that you have different detectors around a single sample stage? I think you partly have that already. That you don't need to change your environment, the position, but you can measure different properties basically at the same time.
Yeah, and that you have temperature cameras, and that you have sensors for acoustic behavior, and that you combine these different sensors and combine this with the imaging, and that this gives you additional information which you may not always be able to identify just on the image itself. But by combining that, you're able to look at certain positions of interest. For instance, we added temperature sensors in our sample, and if you do a scan of 12 seconds, maybe when you do a reconstruction of those 12 seconds, you do not see anything happening. But if you look at where the temperature is changing inside our sample, indicating a small event, you can then focus on that small event in your CT data and reconstruct everything before and after the event, and then see what is happening. So it's by combining different sensors and CT that you will get new insights.
Andreas, we have two more questions, and the time will be up in a few minutes. But just one.
Let's quickly try to do these two more questions. So Leila Hashemi has another question, and she's asking if it is possible to do cyclic injection and production in one sample to mimic realistic storage and production processes using CT.
Yes, I think it will be challenging, a challenging setup. But if you are able to take into account sample size, have contrast, be able to have control of the process, and depending also on the speed of the process, a lot is possible. It just requires trial and error, I would say.
And then Sorin has a follow-up on his previous question on precipitation layer, and is asking if the layer is growing slower compared to the movement of the fluid-fluid interface. Is it still possible to visualize that?
Then it also depends if you have an X-ray contrast between your between your precipitating layer and your fluid, and so it will all depend on the contrast that you have, the resolution that you want to see, and your sample dimensions.
Okay. Is there time for the last one, the very last one?
Yes, please go ahead. That's
okay.
Andreas, you could continue till midnight, but I need a kind of
So Mustafa is asking, following the answer of you, Veerle, concerning the gray level issues, I would like to confirm that the matrix is stable. How does the subtraction solve the problem?
Because what we typically do is we first do a high resolution scan of a stable situation, which is without liquid, and then we add liquid, for instance. And if you just have a scan with liquid inside your sample, you are not able, if you do not have prior knowledge, you are not able to say this grain has a microporosity which is now filled with the liquid, or this grain just has a certain gray value which is related to the average atomic number of that sample. But if you have a grain which is, before it is with liquid, has a certain gray value, and after with liquid has a different gray value, then you know that it consists of microporosity. While if you do not have this combination, you will never be able to say that it is microporosity or that it is just a grain with another composition. And that is why we combine the two to say something about porosity, microporosity, and composition.
Thank you very much. Thank Andreas, Veerle, and also all the audience attendees for the great questions, discussion sessions. We should end any talk, including Veerle's. You should also take rest, I guess, for the rest of the day. Thanks a lot. Again, I would like to also take the chance to announce our next week speaker will be Professor Rick Kalaternik. Rick is from University of Alberta, you all know, and he will be speaking about 3D printing and how can that help understanding multi-phase flow processes in porous media. Also note that Interpore conference will happen online this year again, and remember to register. There will be many of these discussions about porous media, different aspects of it also to happen online. Thanks everybody. Until next week, stay happy, healthy, and tuned. We see you all next week. Thanks all. Veerle, thanks again one more time.
Thank you, thank you.
Heel erg bedankt.
Graag gedaan.
Andreas, dank u wel. Thank you. Bye-bye.
Okay.
Bye.
Cheers. Bye.
Bye.